You may remember that when I closed the last lecture, I tried to develop an application of a stochastic model in the PC in just 5 minutes, and I did not succeed because of time limitation. I think it is important that we try together to set up, to estimate the parameters, to calibrate a stochastic process, and therefore I think that it's worth getting back that exercise. I will do so at the end of this lecture. Now I'm introducing techniques for solving problems that are given by maybe lack of satisfaction of the assumptions. Therefore, I'm introducing a couple of techniques that allow you to resolve the lack of fit of the model, and then we are ready for a full application, which at the end of this lecture I will try to perform at the PC by just repeating what I started the last time. So this will give you an overview of what we are doing today. You may remember that we were talking about stochastic processes, and in particular we considered autoregressive processes. And autoregressive processes, as you remember, they are written in the general form xt. I used the subscript, or did I put t between parentheses? Was like this or like this? Top or bottom? I just want to be consistent. I think I used this one. Am I correct?
The first
No?
one.
The first one. Fine. So, the general form in which we can write an autoregressive process, let's say an AR1 process, autoregressive first order, is phi1 x t minus 1 plus epsilon t. And we specified, as we discussed, the underlying assumptions, and in particular, we underlined that two important assumptions are stationarity and Gaussianity. Now, I think I anticipated that these assumptions are, strictly speaking, never satisfied. So the question is, what to do if they are indeed not satisfied? And for Gaussianity, first of all, we should check whether or not the assumptions are satisfied. And for stationarity, this is a bit of a problem, because in statistics, there are no tests, no formal tests for checking stationarity. There are some situations, especially when dealing with the climatic variables, which suggest that no stationarity is present. But strictly speaking, we don't have any test. So, for stationarity, we have to proceed by intuition, by perception, expert knowledge, to identify patterns that may be responsible for non-stationarity. And let me give you a couple of examples, and I think the situation will become clear. I already anticipated that our time series in hydrology are affected by seasonality, which is given by the periodicity of the weather. And seasonality, of course, what does it mean? It means that, for instance, the average values, the mean values of river flows are changing along the year. Your expectation for river flows is different in April with respect to the summer or the winter, because you know that for many rivers that flow here, during summer we have the drought period, and therefore your expectation suggests that the average value of the river flows is low. Instead, during April, May, usually we have the high flow period, and therefore our expectation is for higher river flows. This is clearly an example of non-stationarity. So when you feel that non-stationarity, that seasonality is present, and as a matter of fact is always present in hydrological variables, this is an indication of the presence of non-stationarity. So it means that the assumption of stationarity is not satisfied. Another example is given by, for instance, diversions of rivers. You know that when we build dams, because this was an activity that was very frequent in the past, more than now. When we built dams, the first concern when you build a dam is whether or not there is enough flow to fill the reservoir. And if you are concerned that there might be not enough flow, a usual solution is to divert the flow from neighboring rivers, neighboring watersheds. And therefore it's clear that if you have two rivers with two different river basins, like this for instance, eventually flowing into the same lower reach, if you build a dam here, in order to fill the reservoir, which may extend like so, very often you get the water from the neighboring catchment and you bring the water through a tunnel in the neighboring river, which means that you realize a diversion. Of course, diversion from the time instant in which you start to operate the diversion, then you introduce a non-stationarity in the time series. So this is another clear example. Or another example is, for instance, deforestation. If you increasingly reduce the part of the river basin that is covered by forests, then typically you have a change, a progressive change in the river regime. This is another example of non-stationarity. So basically what you should do is try to identify reasons for the presence of non-stationarity. If these reasons are reasonable, then you have to do something to put yourself in the condition of applying this model. If you don't feel that there are clear signs of non-stationarity, so if you feel that the time series might be stationary, then you go on. But once model parameters are calibrated, you can make some checks to verify that indeed the series is stationary. But there are no statistical tests. So let's suppose for now that you assume that the series is stationary and you go on with the calibration. I mentioned the possibility to check the parameter values of autoregressive processes, and in particular of the AR1 process, to check the parameter values to verify that the stationarity assumption is a suitable one. And in particular, you should check that, I'm not sure I already mentioned this requirement to you, I think not. You should check that the absolute value of phi1 is less than 1. Because if you have phi1 that is greater than 1, strictly speaking is less or equal. If you have phi1 that becomes greater than 1, this is a clear sign of non-stationarity. We are not discussing in the details. We are not discussing why this is so. I just would like to mention to you that if phi1 is greater than 1, it would mean that you start from a given observation, like here, and you multiply this observation to get the next one, you multiply it by phi1. If phi1 is greater than 1, then you get a value that is on average higher. Of course, there is the influence of the noise also, of the epsilon, of the error. So you should also add the error here. So it's not true for sure that your observations are increasing in value, because the error may compensate, but on average the error is 0. And therefore on average you get indeed an increase. So you get a series that goes like so, because on average you have an increase. Sometimes you have the error that compensates, but on average you have an increase. This means that the mean value is not constant. Instead, if you have the opposite situation, this is given by phi 1 greater than 1, if you have the opposite situation, remember that this series is zero mean by assumption. So if you start from here with phi 1 that is lower than 1, what do you get in the long period is something that converges to 0, to the mean, and therefore your mean is constant. So this helps you to understand why there is this requirement. That can be proved also mathematically, but we don't want to go into the details. So basically, if you assume that the series is stationary and you calibrate your model, you should check, besides all the other checks on the independency of epsilon, Gaussianity of epsilon, etc., you should also check that the parameter is compatible, the parameter value is compatible with the stationarity assumption. Okay, and what to do then when we identify reasons for the presence of non-stationarity? Let me talk about seasonality, because this is, as I said, always present. So we have to know how to manage, how to solve the non-stationarity induced by the presence of seasonality. What does seasonality mean? It means, again, that the average value of the river flows is not constant along the year, it's changing along the year. Therefore, we have to adopt a solution to make it constant. We are talking about the average. In principle, seasonality means that all the other statistics of the data are affected by periodicity, not only the average, but also the standard deviation, also the autocorrelation function. In principle, any statistics of the data due to the effect of seasonality is changing along the year. We are mainly concerned by changes in the mean, less concerned about changes in standard deviation, because they are not as evident, not as significant as the changes in the mean. So our first aim is to resolve the problem of the mean, therefore making the mean constant along the year, stationary along the year. So let's concentrate on a very simple method to make the mean value of our time series, like river flows, constant along the year. And then we will also see how to make constant the standard deviations, and then that's it, because we don't go into more details. Okay, about the mean value then. How can we check the progress of the mean value of the time series along the year? There is a simple method. Let's suppose that you have 10 years of observations to use. You can simply compute the mean of the observations in each calendar day. So let's start from January 1st. You have 10 years, so you have 10 observations collected on January 1st. You can compute the mean. So basically what you should do is to list all the observations in a table in which you have the years that are given as columns and the observations, let me think about it. If I start from 1 and I go to 365, the years are the rows, sorry, and the observation, the intra-year observation are given as columns. Okay? So you have observation of each year given in columns. You put each year in a different column, and therefore along the rows you have the observation collected in the different years for each calendar day. So in this case, this is day 1 of the year, January 1st, and you get the observation collected on January 1st in each year. And you go down until 365. Let's say that the leap years, February 29th, are removed, because of course the leap years, you don't remove all the leap here. You just remove the observation collected on February 29th. This is the usual procedure, because otherwise it becomes a problem, of course. Okay, then you can estimate, here you compute the mean, and you get, in the final column, the mean value of the river flows observed in each calendar day. Good. Then one may want to plot these observations. And therefore, if you refer to an Italian river, a river located, for instance, in the Emilia-Romagna region, you can just plot, let's call it ST, which means S stands for seasonal, against the day of the year. You can plot the average value, the mean value that was computed here, for any day, and then you get something like that. This is a typical picture that you obtain for the Po rivers, for instance, at the closer section, so close to the sea. You get this picture, which shows that you have a peak in late spring. Usually this peak for the Po river at the closer section is around May, June. And then you have a second peak in November. And talking about the mean values, you would see that the first peak is higher than the second one. If I have time later on, I will show you some graphical representation. And while we know that the most severe floods occur in autumn, but if we look at the averages are higher in June. Because in June, May, June, we have the highest flow volumes for the Po river close to the delta. While the second peak in volume is less pronounced, but the individual floods are more severe in autumn, as we know. Sometimes it happens that the Po river experiences floods in June also, but it's infrequent. Okay, usually, indeed, when you compute these averages and you put them in a graph, you find a picture that is not as smoothed as this one. It's more variable, it's something like this. Why that? Because if you have just a few years of observation, of course there is uncertainty in the estimation, which originates some variability. And therefore, if you want to get a representation that is physically meaningful, you need to smooth the time series of the mean values. Smoothing can be done, for instance, by adopting a moving average. This is, by the way, not strictly necessary for us. It's just because if you plot it and you show it to people, of course, it's not very meaningful. A periodical component, a seasonal component that is very much fluctuating, is not really meaningful. Because, of course, the average flow on May 31st should be very similar to the average flow on June 1st. You can't allow different mean values for physical reasons, of course. Okay, then, this is, what is this? It's the progress of the mean value of river flows along the year, which is clearly non-stationary, which means that the mean value is changing. Now, how can we resolve this problem? Very simply. You resolve this problem by deseasonalizing the time series. Deseasonalization, I will repeat later. Let me now try to make the concept clear. Deseasonalization of the mean values can be done by simply subtracting to each observation the mean value of the data observed in the same day. So if I have this observation that was taken, for instance, on April 20, which is the mean of the data collected on April 20, what I have to do to deseasonalize the series is to subtract to each observation collected on April 20 the respective mean value. And this can be done, it can be written down in this way. Let's call the deseasonalized series Y with the symbol Y, and let's put two subscripts. One is the classical T, the second one is J, where J indicates the day of the year. So 1 less or equal to J, less or equal than 365, while T is varying between 1 and capital N, where capital N is the total number of observations. So let me indicate the deseasonalized series with, again, a double subscript. One is the classical T, and the second one is indicates the day of the year in which the observation was taken. Then I can write this Y as X. Let me indicate X again as with the two subscripts minus Sj. Sj is this seasonal component that I computed here. Let me put then for to make it consistent, let me put St in this way by using the subscript. So if you subtract from each observation the average that was collected in the same day, then you get the deseasonalized series. Fine. The series Y that you obtain has a constant average along the year. So we remove the non-stationarity in the mean. Now, what if we want to remove also the seasonality in other statistics, like standard deviation? What we should do, if we want to remove, for instance, the seasonality in the standard deviation, what we should do is to compute the periodic standard deviation. In the same way as we computed the periodic mean, we should compute the periodic standard deviation. Therefore, obtaining a series of sigma t, which you can plot, and you will see that the progress is more or less similar to the progress of the mean. You would notice that when the mean value is increasing, also the variability is increasing. You would notice also much more variability in the estimates of the periodic standard deviation, because the estimation of the mean is affected by less uncertainty than the estimation of standard deviation. The mean is the less uncertain statistics that you can compute for a time series. The standard deviation is affected by more uncertainty, which is given by the fact that you square, you raise to the power of 2 the difference of each observation and the respective mean. When you compute the standard deviation, you may remember that at a certain point you square a difference, and by squaring you increase the uncertainty. Because of course if there is an error, it is squared. This is basically the reason why you have more relevant uncertainty, but in any case, of course, you can compute this periodic component, and then if you want to make the standard deviation constant, if you want to deseasonalize also the standard deviation, what you have to do is just to divide this difference by the standard deviation that was estimated for the same day. So these are quite simple transformations that we usually take because, as I said, seasonality is always present. For seasonality, that's it. There is some remark that I would like to make, but I think it's better if I make the remarks with the PC and by projecting some graphs. But for seasonality, that's it. So, this seasonalization, we are done. Let's just keep in mind that we always need to perform it. But let's say that we are done. Okay? Now, second problem, non-Gaussianity. First of all, how to detect it? For non-Gaussianity, there are a lot of statistical tests that can be applied. There are many of them. The reason why there are many and not just one is because the efficiency of the test is not perfect, so it's better to use more than one to get an overview, a more comprehensive overview. I just would like to introduce to you one test, which I guess you already know because it's the Kolmogorov test, which is very simple. First of all, you already know how to estimate, for instance by using R, the probability density function of your time series. By plotting the probability density, you get a first glance, a first idea of the most suitable probability distribution for the data. One thing that you already well know is that the Gaussian distribution is symmetric. So if you get a probability density function that is like so, this is clearly asymmetric, symmetric with respect to the median, so the highest point of the density. This picture for the Gaussian distribution should be symmetric with respect to the vertical axis that I drew, which is passing for the highest abscissa of the density. In this case, it's clearly not symmetric, so it's already clear that it's not Gaussian. But this is just a necessary condition, it's not sufficient. Not all the symmetric distributions are Gaussian. So even if you plot your probability density function and you find something of very nicely displaced like so, you should be aware that the series still might be non-Gaussian. But in any case, if you get an asymmetric distribution, which you get very frequently indeed in hydrology, you for sure know that this is non-Gaussian. So how to make a rigorous quantitative check of Gaussianity? This is possible. It's not like no stationarity. This is possible. So this is the perception. With no stationarity, we just have the perception. And a check a posteriori with the parameter value. In this case, we have the perception, but we also have statistical tests. As I said, several. And let me just mention the Kolmogorov test, which is very simple, that can help you identifying non-stationarity. How to perform the Kolmogorov test? First of all, you should compute the cumulative frequency of not exceedance of your variable. What is the cumulative frequency of not exceedance? It is given by, we already know this, but you can compute it by putting the data in a column in increasing order. So this is the column of your data that you can put in Excel or in R, and you sort the data in increasing order. And then you put here an index, a progressive index, which starts from 1 and arrives to n, where n is the sample size, the number of observations. And if you compute here I, where I is the index that I just indicated here, divided by n plus 1, this is an estimate of the cumulative frequency of not exceedance. So it's very easy to compute it. Now, what we want to check now? We want to check if the data are Gaussian. If they were Gaussian, we could estimate the probability of not exceedance of each observation by using the Gaussian distribution, whose parameters are given by the mean of the observation and the standard deviation. You remember that the Gaussian distribution has two parameters, mean and standard deviation of the data. I have the data, I can compute the mean and standard deviation. So I can go to R and I can ask R to give me the probability of not exceedance of each observation accordingly to the Gaussian distribution. So I can compare this difference. Again, this is the frequency of not exceedance, this is the probability of not exceedance given by the Gaussian distribution. And if you remember at the beginning of this treatment, statistical treatment, I said that probability should be a very good approximation of the frequency of not exceedance. If probability is computed correctly, it should be very close to the frequency of not exceedance. Therefore, it means that if the Gaussian distribution was the correct one for our data, this difference would be 0. Not 0 because there is uncertainty, but should be very small. This difference should be very small. Let's compute the absolute value just to get rid of the sign. This difference should be close to 0 because, again, probability of not exceedance should be a very good approximation of the frequency of not exceedance, if the Gaussian distribution works well, of course. Now, indeed, this difference will never be 0 because of uncertainty and also because possibly the Gaussian distribution could be not adapted to describe our data. Therefore, if the Gaussian distribution is not good, we will obtain values for this difference that are not close to 0. So we have to fix a limit. First of all, let me take the max of this difference because I am interested in the max. I am interested in the max. So let me take the max, and then I should fix a threshold value for this max, such that if the max exceeds this threshold value, I say no, the Gaussian distribution is not good. Conversely, if the maximum is less than the threshold value, I'm entitled to say, okay, the Gaussian distribution works well. So the test is computed in this way. This is what is called the test statistics. Then I have to compare the result, the maximum, the test statistics, with the threshold. What is the threshold? I give you a reference value, which is 1.36 divided by, I think, I don't remember well. When I turn on the PC, I will check. I don't remember if there is a square root here or not, so please keep this doubt. But this is an indication which is rough. It's not really precise. This is a rough indication for the threshold value for the test at the 95% confidence level, which means that the test has 95% probability of being correct. This is not really a very formal statistical statement, but we are engineers, so let's take this statement for correct. Test at the 95 confidence level means that the test is correct with a probability of 95%. And please, I will solve this doubt when I turn on the PC. I don't remember if there is a square root or not. But in any case, let me say, please keep in mind that if you want to be more strict, you should also change this coefficient depending on the sample size. And there are tables on the web. If you Google for Kolmogorov test, there are tables on the web that give to you the correct value for the threshold depending on n. This is a rough indication, because you see here that the threshold depends on n only through the denominator, not through the coefficient 1.36.